Hello, today we're going to be going over the second project. This is our M&Ms project. You'll notice, right, as it says at the top, it is due April 30th. Just like the previous project, you can email this to me or upload it to the Dropbox in D2L. If you're in my in-person class, you'll just turn it in during class. So I'm just going to run through it, kind of show you the different steps, talk about what the expectations are. That's the idea for this section. So first off, make sure you're answering the questions. Answer completely. A lot of these are going to be statements. Use full sentences. I think a few people on the exam were kind of shortcut a little bit much to the point where their answer didn't have much of substance. So use a complete sentence when you're explaining your answers. Round all number values to the nearest percent or two decimal places. You'll have z-scores that won't be percent. They'll have like two decimal places, and you'll have percent numbers you'd round to the nearest percent, unless it says otherwise. I think there's one or two questions where they tell you something else, so you'll just have to follow the directions on those questions. Okay, to do this project, you are going to go and buy some M&Ms. It needs to be either milk chocolate, peanut, kids minis, dark, peanut butter, or almond. It has to be one of those kinds. You can't go out and buy something else. It needs to be one of these kinds. You'll see why a little bit later. And you need to count at least 100 of them. So you have to count at least 100 of the M&Ms, count how many blue, orange, green, bright yellow, red, and brown you have. And you'll use that data and you'll actually fill out this frequency chart down here. So you get the frequency of all the different colors, and you'll calculate the relative frequency. Remember, that's just the frequency divided by the total. Your sample size, N, is your total. And then the cumulative frequency. Remember, cumulative frequency is the running total, so you just start off with the top one and you add up as you go down. That's your cumulative frequency. You're going to pick, of course, your type, whatever kind you buy. Just to note, there is no plain M&Ms. I have so many people put plain on here, and I think they're thinking milk chocolate is plain, but no, milk chocolate is milk chocolate. There is no such thing as plain M&Ms. So if you have milk chocolate, put milk or milk chocolate. The color, you're going to pick a color from your set that you're counting, and you're going to do your project with that color. Okay, so you buy your M&Ms, you need to have at least 100. If you're buying something like peanut M&Ms, like a small bag, that's a regular like bag you grab at the gas station checkout of peanut might not have 100. If you grab like the milk chocolate or the minis, then you're not going to need as big of a container to get 100 because they're smaller M&Ms. If you want to do something like the almond or the peanut, you might have to get like a share size bag. You don't have to count the entire bag, you just need to count at least 100. If you do more than 100, that's great, that's awesome, I love that, but you have to do at least 100. You can't do anything less than 100. If you get too small of a sample size, it makes some of the problems later on just not work very good. So you want to make sure you have at least 100 in the bag you count. It's okay for you to share a bag with someone else, just you can't count the exact same M&Ms. So if you come up with the exact same count as someone else, I know something's up, that's kind of a big red flag. You can share, you both can grab a handful out of a bag, even if you just get most of the same handful, but grab some extras so you're not the same count. But you shouldn't have the same count as someone else. You should have your own count of M&Ms. Okay. So like I said, you're going to get your bag, you're going to count, you're going to get your frequencies, kind of get relative and cumulative frequencies. Then we're going to use the frequency data to do some calculations. We'll find mean, mode, and mean. Remember, these are measures of center, so you're trying to figure out kind of what's typical, what's average. So you look at, for the different colors, what's the average amount of that of those colors. So you have to put an order, find the median, find the mode. A lot of these won't have a mode because you might not have the same number of more than one kind. If they all have different numbers, so of course there's no mode. Mean, you can of course add them up, divide by how many there are. So you'll just do that with the frequency data, and then you move on to the next slide. Here you're going to do some measures of variation. So remember, variation, we're measuring the spread. Find range, which is the top minus the bottom. So you take the largest value, subtract the smallest value, you get your range. Your standard deviation, remember when you find standard deviation, first you have to find the deviation. So you're going to have to use the mean you found on the previous page. Subtract that from each of the values. You subtract the mean from each number. Then you square those results. And when you get those squared, then you add them all up, and then you divide by 1 less than the number of values. In this case, since we have 1, 2, 3, 4, 5, 6 colors, you would divide by 5. So here you would divide by 5. And then the last thing you need to do is square root. I know a few people that were forgetting to square root on the test. So you do the deviations, you square, you sum, and then you divide by 5 because n is 6 and n minus 1 is 5. That's why we're dividing by 5. And then you square root. And that'll give you your standard deviation. Again, that's a measure of spread. Next, I want you to give the 5-number summary. Remember, the 5-number summary is the minimum value, the lower quartile, the median, the upper quartile, and the max. That is the 5-number summary. So you have to look for the smallest value, the biggest value, the median, which is the middle, and then you do the lower and the upper quartiles. Remember, the lower quartile is the median of the bottom half of the data, and the upper quartile is the median of the upper half of the data. And then you draw your box plot here. I didn't put numbers in here, so you can add your own numbers in for your values. Remember, you have a line at your min, line at your max, line for your lower quartile, median, upper quartile, and then connect like that, and that is your box plot. So it should be the min, the max, the lower quartile, the upper quartile, and the median. And of course, make sure you label your box plot, so that I know what the values are, because sometimes they don't end up right on the number line dashes, so it's good to know what the values are. So make sure it's labeled. Okay, so that's just using your frequency data. Again, you're just using the frequency data to calculate, spread and the measure of center. Then after that, we get to move on to the real heart of the project, which is actually doing a hypothesis test. So we're going to set up a hypothesis test so we can actually check and see if we agree with the claimed values, percentages from the project. So say I'd done my project and I had picked, let's say peanut M&Ms, and I did blue as my color, and blue peanut M&Ms are, and say I did for my frequency, I got for my blue frequency, I got 18%, right? I'll just do an example, just made up an example. I'll get my type, my color, 18%. Then on this part, p hat, that is the percent I got. That's your sample percentage. So from the sample I took, 100 M&Ms, is not that big, out of the millions and millions of M&Ms they make. I just took a little sample, 100 M&Ms, sampled those. I looked at my percentage, I got 18%. Then I look at this chart, and here are the published values. This is the reason why you need to buy one of these kinds, because I only have the data for milk, peanut, kids minis, dark, peanut butter, and almond. So if you go out and buy pretzel M&Ms, it's not on the chart, you can't do the rest of the project. So don't buy pretzel M&Ms. Don't buy anything that's not one of these types. It has to be one of these types. So you buy one of these types, do your project, you look up your sample percentage, calculate that, then you look up what they say it should be. So for peanut blue, they say it should be 23%. So that's what goes down here. So this percentage is the percentage that they published, the value that Mars Company told us. These are all from Mars Company. So they said this is how much is in these bags. In peanut M&Ms, there should be 23% blue. Okay, then we're going to say which one's larger. Well, in my case, the published value is larger. The published, and we're going to call that P, so P is larger. P hat, again, is a sample. P is the population value, the value that they published. We're going to do a little bit of Mad Libs. So Mad Libs is just fill in the blank. So here, this is going to be the claim. So we just got to fill in with appropriate words. So here, the percentage of blue, because I picked a blue, yours will be whatever color you pick. And I did peanut M&Ms, so I'll put peanut. So it'd be the type you picked. M&Ms in bags sold by Mars Inc. And I'm going to say is smaller because I only got 18%, and they said it should be 23. So I'm going to say it should be less than. So I'm going to be less than, or smaller than, less, I should just say less than, 23%. So they claim 23%. That's, I guess I have 20% there. I don't know why I keep writing stuff that's already there. I just need the 23 and less. So I think it's less than 23% because I only got 80% of my sample. They got 23% on their published value, so I'm way low. So I say, okay, I think that should be less. And if you get anything below, you're gonna say less. Of course, anything if you got above. So if I'd done this and got 25% instead of 18%, then I would say it was above. It should be greater than. Note, if you get to this point, if you're doing this and you get to this point and your two percentages match, you need to pick a different color. You can't do this project and say, oh yeah, I got 23%, they got 20%. I say they're right, and then be done. But that would just defeat the purpose for the whole project. So when you get to this point, if you get your color and it matches theirs, then go back and pick a different color. You sampled a bunch, just find a different color that doesn't match up with what they got and do that one instead. you might have to go back and change, instead of doing blue, you might say, okay, well, my blue percent was like right on, so I'll do my orange. Doesn't happen very often, but every once in a while, go back and start over with a different color. I really just start from here because the rest of the stuff it doesn't affect, but here it does. Okay, now that I got my claim. So a claim is that the percentage of blue M&Ms is less than 23%. I need to write my null and alternative hypothesis. Remember, null is always going to be a statement of equality. So you're going to say that the actual percentage of blue M&Ms is equal to their claimed value. Remember, we always assume their claimed value is correct, and then we test it and we try and disprove it with our data. So I'd say it's equal to that, 23%. Yours will be whatever percent you have from the publisher, and it depends on your color and stuff. But you make a claim about the percentage of all blue M&Ms. Your null hypothesis is going to be about all the blue M&Ms, and it's going to say it's equal to the claim value. The alternative, it's going to be less than or greater, and then it's going to depend on what happens for you. So my value was less than they said, so I'm going to say I think it's less than. So my alternative is going to be less than. But if yours is bigger, it'll be greater than. So it depends on what you have here. If you do less than, and it's going to be less than, like mine. If you're greater than, it'll be greater than. Again, you talk about the percentage of blue M&Ms, and you're going to say it's either less than or greater than that claimed value of 23%. I got something less. My 18% is going to give me evidence to say, hey, I think it's less. I don't know if it's strong enough evidence. We have to test that. That's what we're going to do the rest of the project, to figure out, is it this enough evidence to say it's not equal to, it is actually less than. That's what we're going to check. But that's our hypothesis. Our hypothesis is always going to be inequality for null and either less than or greater than for alternative. Okay, so now we got to test this hypothesis. We got to see, can we reject the null equality, and can we prove the alternative that it actually is less than in my case. So to do this hypothesis test, we're going to test it at the significance level of 5%. We mentioned when we were doing the notes that there's a 5% level, so if you have a probability of less than 5%, then you can say you can reject the null and you have moderate evidence. And if you have less than 1%, then you have strong evidence. We're not going to require strong evidence. We'll just say if you can get a probability less than 5%, we'll call that enough evidence. We'll reject the null. Now to test this, to get the probability value to test this, we first need to calculate a z-score. So we're going to calculate a z-score. Now we're not going to do it with the same formula you've been using on like the test. This is a formula, this one's for specifically like percentage situations. So here we're looking at like the percentage of M&Ms. The z-score we were using on the test was actually the z-score for means. When you were looking at averages, here we're looking at percentages, not averages. That's why it's a slightly different formula. So we're going to calculate what's called the test statistic. It's a z-score based on our sample data. And to do it, we're going to use this formula. You're going to take p hat minus p, and you're going to divide that by all this stuff. Be careful when you type this in, make sure on the top you put a parentheses, if you're doing it in your calculator, because you want that subtraction to happen before the division. Also make sure that all this stuff down here is inside the root. So you want the p times 1 minus p over n. You want all that to happen before you do the square root. So that should all be inside the square root. Also, make sure you use the decimal values for these numbers. The reason why it doesn't work if you use the percent form, so like say p was 23%, you end up with 1 minus 23, which is a negative number, and you can't square root negative numbers. It won't work. It'll actually mess up this calculation really badly. So you need to use decimals. Instead of using 23%, I would use 0.23. And then you can do that, because 1 minus 0.23, that's a positive, and it works. So make sure you're using that. N here is your sample size. So when we're doing our first frequency table, you notice I put that right here. This is the N that you're going to be using for a lot of these things. So anytime you need N, that's going to be your sample size. It should be, greater than 100, greater than or equal to, I guess you couldn't do it exactly 100, but it's more fun if you do more. So if you have a number bigger than 100, that should be part of your formula down here. That's your N, is that number that's over 100. It's the sample size. It's how many you counted. That's what N is. It's the sample size. So you'll do this formula. You'll get a z-score. So you get a z. You find out what it is. Remember, z-scores, you typically expect them to be between 3 and -3. So it's going to be somewhere between -3 and 3. If you get something bigger than 3 or less than -3, that's a good sign you probably did the formula incorrectly. That's when you should double check with me. That's kind of a big red flag. It has happened in the past. In the past, people have had their values mismatch so badly that they ended up with a z-score beyond 3 or beyond -3, but it's very rare. So if that happens for you, that's something where you should double check. Most likely you're probably just not doing the formula correctly. So you should get a number somewhere between 3 and -3. Again, a negative z-score means you're below average. A positive 3 score means you're above average. That's what this would do. So yeah, we look at this, we'll calculate your z-score. Now what you need to do is you have to take the z-score, this test statistic, you have to use that to find the probability, the likelihood of getting this result. So remember we said that the less likely your result, the more reason you have for rejecting the null. So what we're going to do is we're going to take the z-score and we're going to find the p-value or the probability value. You're going to use the standard scores and percentiles chart from your formula sheet. So on the formula sheet on the bottom, it has that chart that has all the z-scores and the matching percentiles. Well, you use that. So you'll look at the chart and you'll find the z-score, whatever it is. I'm going to make up a number. Say my z-score is 1.3. I don't really know what it is. I'm just making up a number. So this might be silliness is probably, or actually it's probably going to be like negative 1.3. Say that's my z-score. Then pull up my chart. I didn't bring it with me, so I don't have my chart right now, but I'd look it up and I get a percentile. So again, I'm going to make a percentile. This is probably not right. Say I get like 4%. That's not going to be right because I didn't look this up. But that'd be my percentile. I get that percent from that percent score. Now, because I'm doing the percent, I'm doing less than, I do want the percentile or the percent below. Remember, percentile is the same thing as percent below. And so I'm happy with this number. If yours, instead of doing less than, you were doing greater than, then you'd actually want the percent above, and you'd have to subtract from 100. So like you would end up with like 96% because you're doing, when you first started, and then you subtract from 100, and that's how you get your 4%. So if you're doing like greater than, the chart would give you something like 96%, and you'd have to do 100 minus 96 to get your actual value of 4% or something like that. And I don't know what the number is going to be because the numbers are going to vary from person to person. But that's kind of the idea. So if you're doing percent below, if you're doing less than, you just look up the number of the chart, you're done. But if you're doing greater than, you have to do this whole subtraction thing. So that's why you have to be careful which one you're doing if you're doing less than or greater than. I have a note here, right? So if it says less than, it's just a percent below, it's a percentile. That's it, you're done. If you're doing greater than, p-value is percent above. And that's a reminder that percent above, you have to subtract to get the top side. Because remember this standard score percentile chart, percentiles are percent below by default. That's what a percentile means. So if you're getting less than, you just look up the chart. If you're doing greater than, you have to subtract from 100. Okay. Now this percent is your probability. It's the likelihood, it's the chances of getting your result that you got. The smaller the chances, the less likely, the more extreme, the better evidence we have for rejecting the null. So we're going to compare it, like we said, at the significance level of 5%. We're going to compare that and decide whether or not to reject. So like here I got 4%. Well, 4% is less than 5%, which is actually telling me that I should reject. And that's how you'll decide. If your chances, your probability value, the p-value is called the probability value, if it's small enough, then you can reject. But it has to be less than 5%. That's the cutoff. Anything above 5%, we're going to say we're going to fail to reject. We didn't have strong enough evidence. That's what happens when your value is too close. You have to be extreme enough. You have to be far enough away. So the p-value is small, then the probability is small. That's when you get to reject. Once you get done with this one, you have to answer number 13. Basically, it just says, based on this, do you have sufficient evidence to support the claim? And in my case, I was able to reject the null, which was the equality statement. So I rejected equality, which means that yes, I have enough evidence I can support the alternative, support the claim. So here in this case, I would actually say, yeah, I have reason to show that it actually is less than the published value. They said 23%, I got 18%, it was so much less. I can actually show that, hey, my data says your number, your 23% isn't any good. It actually should be less than that from my sample. If you fail to reject, of course, then that's when you don't have enough evidence, right? So failure happens when you don't have enough evidence. In that case, you would fail to support the claim. Remember, you cannot prove the null. I had a few people doing that on the test. Remember that the whole point of this is you can support the alternative, you cannot support the null. So you can't prove it's equality. You never do that. You don't say, oh yeah, it actually is 23% because my value is too close. And you say, I didn't have enough evidence to support that it was below 23%. I couldn't prove that because my evidence wasn't extreme enough. Just because you get a value close to 23, like 22%, doesn't mean actually it is 23. It could be 22 or it could be 21. all you can say is you didn't have enough evidence to disagree with 23. Your value wasn't extreme enough. Okay, we're going to test it this way, but we're actually going to do this test a couple more times. We're actually going to test it out a couple different ways, and there's a possibility you might get different results. So that's why we're going to keep trying this different ways. So the next way to do it is we're actually use a confidence interval. So to build the confidence interval, the 95% confidence interval, we're going to use the margin of error formula that we did during class. It's from your formula. So you're going to use that 1 over root n, and then you're going to write this answer as a percent and with 1 decimal place. So this would be the one example where instead of a percent round to the nearest percent, I don't want you to round it to 1 decimal place. Margin of error is 1 over root n, where n is your sample size. So you go back to that first page, that's what this is going to be. So n is going to be some number over 100 because it's the number you sampled. So for example, if I had 105, I'd have 1 over square root of 105. You get some kind of decimal number, should be like 0.09, blah, 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 blah. And you'd want to turn this into a percent. So you move the decimal over 2 spots, so you get like 9 point something, and you just do 1 spot after the decimal. So your percent shouldn't be anything more than 10%. If you get anything higher than 10%, you're doing it wrong. Your percent should be less than 10% or less. That's the rule for this one. So 10% or less. I don't want a really big margin of error. That's part of why we had to do this big sample size. The bigger your sample size, the smaller your margin of error. So if we had counted 1,000 M&Ms, then our margin of error would be like 1% or less. So that's why in real life, if they're doing a study, they probably would actually do a bigger sample size. And our 100 is not that big. Okay, once you have the margin of error, you're going to take and you're going to use the margin of error and your point estimate p hat. Remember, that is this value here. It's the value you got from your sample. That's p hat. Please don't use p. You're supposed to be using p hat for your confidence interval. The confidence interval is that wiggle room, that margin of error, wiggle room. So basically, you take what your value is. Mine would be 18%, and you subtract your, margin of error, and you add your margin of error. And it's going to be some kind of decimal number, so it'd be like 9 point something. So here I get around 9%, here I get around 27%. It'd probably be a little bit more and a little bit less, but it'd be close to that. That's your confidence interval, and so you're 95% confident that you get the actual value within this range. So another way to do the hypothesis test is actually to say, okay, does the value that Mars company claimed, is it within this range? And so in my case, because I went up from 9 to 27, well, yeah, that actually includes 23. So 23% is included. So we're going to check to see if the p-value falls within. If the p-value falls inside there, then you say, okay, I failed to reject. No, they're close enough within my margin of error, their value is okay. So in that case, I would fail to reject because the p-value was inside there. If you do this and their p-value does not fall inside there, so like say they had like 28% for the published value, which is not inside this range, then you say, oh, that's not close enough, so I would reject it because it doesn't fall within my allowable range. So we're saying we'll be okay with any numbers inside this range. Anything outside this range we'll reject, and so then we actually have evidence to support the alternative. We can prove that it's beyond what they said. So that's how we're going to check this one. It is possible for you to get a different answer. I just did, right? Because previously I said reject, now I said fail to reject. So they could be the same, they could be different. That can happen. Now this 1 over root n we're using is actually an approximate. It's not perfect. It's just a really simple, easy way to approximate the formula. So we're going to use the real formula this time. So next time, number 17, we're going to do this. We're going to build another confidence interval. First, we're going to find another margin of error, but now we're going to use the actual formula. So this formula has the number 1.96, the p hat, 1 minus p hat over n, and this is the formula. So like in my case, I'd do 1.96 times root, 18% by, turn it to a decimal. Again, don't forget the decimal forms when you're doing these formulas with the p's and p hats. 1 minus 0.18 over n, which, we just said, okay, my example is like 105, but it's going to be around 100 for yours. And you type this in your calculator, making sure all this stuff is inside the root, and then give you your new margin of error. And it'll be a little bit different, not a lot, so maybe mine turns into like 8%. I don't know exactly what it is, but I'm just guessing. So, you can type this and get an exact number, but, this is just an example. So you'll get something else. It might be bigger, smaller. It just depends on, the problem. So I can't guarantee one way or the other. But it's going to be a little different. This is the real, actual margin of error. It's not the estimated margin of error. So this is the better margin of error. This is guaranteed to work better. but it might not work that differently. So we're going to see. We're going to check and we're going to see if we get a confidence interval that is comparable. So we'll do, again, I'd do like my 18% minus 8%, my 18% plus 8%, because here I got 18% was my sample. That, again, that's the p hat, for doing your confidence interval, use p hat, and then your margin of error. So I get somewhere from 10 to like 26%. 23% still in there, so I would still fail to reject. So I'd say, okay, using this new confidence interval, I still fail to reject, because again, I'm looking to see if P is inside that range. If P is inside there, fail to reject. If it wasn't inside there, if it was like 27, 28% was P, then I would actually reject it, because I'm saying, hey, I'm way lower than that. I'm only looking for numbers within this range. Anything beyond that, I'm going to say it doesn't work. Now, how did the two intervals compare to each other? I get so many people trying to say, like, well, the second one is better. That's a given. The second one's the actual formula. The first one's just an approximation. I want to know, how do they compare? Well, what I really look for is, do they give you the same result? In my case, they do, right? The first one said fail. The second one said fail. Yes, the margin, the confidence intervals can be a little bit different size. This one's 10 to 26. The other one's, 9 to 27. Yeah, it's a little bit different size, but in the long run, in the scheme of things, that doesn't really matter so much that they're different size. What matters is they both, contain 23%, which was the published value, and so they both failed to reject. So that's really what matters. Look for, do they both fail to reject, or did one not fail and one failed? So if they do the same thing, does it make a decent approximation? Well, yeah, it did. Because, yeah, the numbers weren't close, but they both ended up with both having the same result. So I could use the 1 root over root n, and if all I've been looking for is whether or not to fail to reject it at all, well, yeah, the approximation worked great, because it told me to fail to reject it just like the actual function did, the correct equation. So that's what you should be comparing. When you're comparing to see if something's a decent approximation, look and see if it gives you the same final result. Yeah, I'm not going to get the exact same margin. That's fine. It's not a big deal, because as long as the margin works, that's what's important. I don't care if it's a little different. Okay, last page. So now our data set, we just said, we did sample 100. That's really not that much to sample, right? A sample of 100 is not that big. So we're going to do this one more time, but we're going to use a bigger sample size. So what I'm going to do is I'm going to collect the data from my class, my in-person class. So I won't worry about trying to collect everybody's from online, because that'd take too long. So I'll collect data from my in-person class by Monday next week. And I'll publish that, I'll put it up in D2L in my lab. I'll get it up there so you guys can see it. And so we'll take this data, this class data that's got like 20 people with 100 each. So it's going to be like a couple, 2,000 M&Ms, a lot better than 100. And we'll use this now and do one more final test. So you'll have a new p-hat from the data, because I'll give you a percentage from this, some new classroom data, and you'll have a new sample size, new n. We're going to go back and we're going to do margin of error one more time with this 1.96 formula. So we're going to use this 1.96 root p-hat and n. We're going to use that formula, but with the bigger new p-hat and bigger n. I guess p-hat could be bigger or smaller. We don't know what p-hat's going to do, but n is a much bigger sample size. We're going to get this for the class sampling data. And you'll build one more margin of error, and then you'll build a confidence interval. So this one's going to be like 2 steps here. You have to find the margin of error, and then the confidence interval. You have to do both in one step. Now that you have one more confidence interval, then you can go back and check one more time. Does it contain P, the published value? And so I'd look and see for mine if 23% was in there. And again, if it's inside there, we fail. If it's not inside there, that's when we reject. So you have to go check again, decide which one to do. Last question, why would you be more likely to trust results from 22 than 19? Well, we just talked about this is a much bigger sample size, right? So when you're trying to do a study, you get a bigger sample size, you have a smaller margin for error, you're going to be more likely to get the accurate result. So that's really what question 22 to 3 boils down to is bigger sample size. That's why we trust it. And that's the whole project. That's it. That's the whole thing. So, you're going to buy your M&Ms, you're going to, make your frequency table, measure center, measure variation, and then you're going to perform, hypothesis tests, build some confidence intervals to perform those hypothesis tests. If you have any questions about this, you're free to ask me. Please do reach out. I've had students come into office hours and finish the whole thing. That's fine. You know, you're welcome to come get help with this. You can ask friends for help. You do need to do your own project. Don't turn someone else's project in. Don't do someone else's project for them. Do your own project. You're totally welcome to get help with the project. That's kind of the nice thing about projects. It's not like a test where you have to do it all on your own. Project is a chance for you to definitely bulk up your grade a little bit by doing this and having time to get it done, time to get help. Notice the April 30th deadline. That's just over a month away. If you took the time and did one question every day from now until the due date, you actually get it done about a week early. And that's pretty reasonable. You know, then you have plenty of time to get it done, all that kind of stuff. One question a day is not that much, especially some of these questions go pretty quick. So I think that's a great idea. Just try and do at least a little bit each day. You know, the first day you just buy your M&Ms and count them. You already got 2 problems done because you pick your type and you counted your M&Ms. So that's pretty good. So it doesn't take a long time to get through this. My biggest warning is don't be the person, 2 days before it's due, trying to get the whole thing done. It's so easy to get hung up. You get down to a problem where you're trying to type stuff in. Maybe you're trying to use like this z-score formula that you haven't seen before, and you're just not using the decimals like you should, and you get stuck. And then what do? If you get stuck there, you can't do the rest of the project. So don't be the person that waits till the last minute. Make sure you are working on this throughout. Give yourself plenty of time. There's no nice big spring break, before it's due to get it done. So you have to do this outside of, in your time throughout. But work a little bit each day and you'll get through it and you'll be fine. So, thank you much. I'll see you on the next video.